So, what I want to look at today are the rational functions. We looked at the parent function for the reciprocal function, and there are some similarities here. With the reciprocal function, we saw that we had a vertical asymptote at the y-axis, and we had a horizontal asymptote on the x-axis, and you saw how that worked. What we're looking at here with rational functions, take that idea kind of one step further in order of complexity. What we're talking about here with a rational function is a function where the numerator and denominator are both polynomial functions. Okay, we have these polynomial functions, and one key to understand initially here is that the rules we're going to look at here are rules for when those numerator and denominator do not have any common factors. Okay, we're going to talk in a little bit about what happens when there are some common factors. But what do we do when there are no common factors? Like we had with our parent function, the reciprocal function, there are going to be often vertical and or horizontal asymptotes. So how do we determine these? Okay? This first part that we want to look at are just kind of defining how we can find asymptotes, because the asymptotes are really what are going to help us shape our graph and shape our sketch of a graph. Okay? First of all, the vertical asymptotes are found when we find the zeros of the denominator. Okay? The zeros of the denominator. If you have a rational function with no common factors, the zeros of the denominator will always give you vertical asymptotes. A second thing here is that the graph is going to have at most one horizontal asymptote. We're not going to have multiple horizontal asymptotes. Okay? And sometimes we won't have any at all. Okay? Now, the way we find horizontal asymptotes is by comparing the degrees of our numerator and denominator. And you'll notice here in the statement up here, n is the degree of x, and m is the degree of x in the denominator. Okay? N is the degree of x in the numerator, m is the degree of x in the denominator. So, obviously, there are only three comparisons that we can have. Either n is bigger, m is bigger, or they're equal. And those three cases are what give us the different situations that we can run into for determining what horizontal asymptotes we have. So first of all, let's consider when n is smaller than m. Okay, in other words, the degree in the numerator is less than the degree of the denominator. If that is true, then the graph of f has the line y equals 0, the x-axis, as a horizontal asymptote. We actually saw that with our parent function, 1 over x. The degree in the numerator is 0, the degree in the denominator is 1. So the bigger degree on the bottom means we have y equals 0 as an asymptote. Okay? That would be true even if it weren't just 1 over x. So let's say that we had, a 4x cubed plus 3, and we had an x to the 4th minus 1. Okay? Here we still have a higher degree in the denominator, so y equals 0 is our asymptote, our horizontal asymptote. Okay? B, here, if the degrees are equal. If the degrees are equal, then the line a sub n over b sub m, y equals a sub n over b sub m, is the horizontal asymptote. And notice here, a sub n is the leading coefficient in the numerator, and b sub m is the leading coefficient in the denominator. Okay, so we're looking at leading coefficients here. Come on, why isn't it erasing? There we go. Okay, so in this case, let's say that we, instead of having what we have here, let's say we had 4x cubed plus 3 over x cubed minus 1. Here the degrees are the same, they're both cubed, so we would say that there's a horizontal asymptote at y equals what over what? 4 over 1, okay? The leading coefficient there is 1, so y equals 4 would be a horizontal asymptote for that graph, okay? Now, the last possibility is if you have a higher degree in the numerator than you do in the denominator. Okay? If the degree on the top is bigger, then you will have no horizontal asymptotes. Okay? That doesn't mean we're not going to have any asymptotes at all. It just means we're not going to have any horizontal asymptotes. Okay? Now, one connection I'll make here is that this actually gives you a little bit of a preview. If you're going to go on and study any level of calculus, you'll learn about limits. Okay? If we take a look at when x is approaching positive infinity, in other words, as x gets really, really big, if we're finding limits, these rules actually still apply. As x approaches positive infinity, all these rules apply to what the limit equals rather than what the asymptote equals. Okay? Same thing if x is going forever to the negative side, approaching negative infinity. Okay? Now, one thing I will mention, and I'm actually going to show you an example of this here, is that horizontal asymptotes behave a little bit different than vertical in one aspect. Okay? They behave a little bit differently in one aspect only, and that is, it is possible for a graph to cross a horizontal asymptote. Okay? But that's only in the middle. It still will approach that asymptote on either end. Okay? So we call it asymptotic behavior of the graph. As it approaches the asymptote, it's going to do that on both ends of the graph. But somewhere in the middle, it is possible for the graph to cross your asymptote. So, for example here, in this case, we have 2x over 3x squared plus 1. So we have a smaller degree on the top, which means our horizontal asymptote is at 0. Okay, y equals 0. For our domain, this is going back. Is there anything that's going to make this denominator equal to 0? No, not any real number, right? I mean, there's some imaginary values that can, but no real number. So the domain is that x can be any real number, right? So x is any real number. So what vertical asymptotes do we have?
None.
None, okay? There are no vertical asymptotes. Now, when I sketch this, if I were to sketch this, you can see here that there is a horizontal asymptote on the x-axis. However, what would you get for a y-intercept? 0. So I have a horizontal asymptote here, but I'm crossing it at 0, 0. Okay? If you were to find some other points, this is what this whole graph would look like. Okay? It actually goes up a little bit. At 1, we're at 1/2. But then it starts to approach the asymptote on this side. Okay? On the left-hand side, it goes down to -1, -1/2, but then it starts to approach it on this side from the bottom. All right? So you can see there's this asymptotic behavior. It's approaching the asymptote, but it did cross it in the middle. And that's where I was saying the horizontal ones are a little bit different than the vertical ones. Yes?
Why is there no vertical asymptote?
There's no vertical asymptote because those are determined by what would make our denominator equal 0. And if I set the denominator equal to 0, x squared would equal a -1/3. So if I square rooted, I'd get plus or minus I times the square root of 1/3. So since that's imaginary, all the real numbers are possible in the domain, which means I don't have any vertical asymptotes. Okay, good question. All right, so I wanted to throw that out there so you could see one that happens that way, because it is a little bit goofy to think of actually crossing an asymptote. But horizontal asymptotes, we're just talking about end behavior, not necessarily the stuff in the middle. Okay? Now, let's try one that's a little more, there are no surprises on this one. Okay? Let's take a look at it. 2x squared over x squared minus 1. All right? 2x squared over x squared minus 1. What would our horizontal asymptotes be? Y equals 2, good. Notice they're both x squareds in the numerator and denominator. So it's y equals, it's 2 over 1. So that's 2. What would the domain equal?
X cannot equal positive 1 or negative 1.
Okay, everything except for +1 or -1. Okay? If you set that x squared minus 1 equal to 0, you'd get x equals plus or minus 1. Okay? Now, as we saw before, the very first thing, the graph of f has vertical asymptotes at the zeros of the denominator. Well, we just found the zeros of the denominator to help us find our domain. So our asymptotes are going to be x equals 1 and x equals -1. We're going to have two asymptotes. Now the reason we find all this is because just with that information we can get a really good idea of what this graph looks like. Okay? So watch this. Let's actually sketch this one. And when I'm sketching, the first thing I'm going to do is I'm going to put my asymptotes on here. Okay, so I have a horizontal asymptote at y equals 2. So we always sketch our asymptotes with dotted lines so we know that's not part of the actual function. And then we also have these vertical asymptotes at x equals 1 and at x equals -1. Okay? That will give us the general shape of this. Okay? Now, a couple of points would be helpful. All right? So the easiest one to find would be our y-intercept. What would our y-intercept equal? 0. Yeah, plug in x equals 0, you get 0 over -1. So I know I hit 0. And here's the thing, I know it can't be going up. I know on both sides it's got to approach these vertical asymptotes, but I know it's not going to approach it going up because I've got this horizontal asymptote here. So I know I've got to go down over to here, and I've got to go down over to here. Okay, so it's approaching. It looks like we have like a parabola in between those two asymptotes. It's not a parabola, but it looks the same. Then, if you understand what happens with asymptotes, with the vertical asymptotes, we can actually sketch the rest of this. When these asymptotes come from zeros in the denominator that have no multiplicity, you will always get an alternating kind of approach. Here, on this x equals 1, we're approaching it from the left, going down towards -infinity. So once we get past that asymptote, it actually jumps up to +infinity and starts coming down, and then we're going to approach the horizontal asymptote from there. Does that make sense? We got an alternating kind of idea here. It's approaching at negative infinity on the left, so it jumps over to +infinity on the right. Same thing here. As we approach x equals -1, it's going down to -infinity. So on the other side of -1, it jumps up to +infinity and then approaches our horizontal asymptote from the top. Okay? Does that make sense? Now, the only time that alternating pattern won't happen is when we have a multiplicity that's even. If you have no multiplicity, or let's say this was x minus 1 cubed, so you had a multiplicity of 3, you're still going to get that alternating pattern. But if you had, say, you know, if this 1 had a multiplicity of 2, you know, like this was x minus, you know, an x minus 1 squared times x plus 1, everything else would be the same, except here, because it has a multiplicity of 2, rather than jumping up to +infinity, it would come from here and approach from the bottom. That's really the only difference. Okay? So just be aware of that. Now, one last thing I want to point out to help you remember. Let's get back to the original. To help you remember our rule for horizontal asymptotes before we look at ones that do have some common factors. This is a rule I hadn't heard of until some of Ms. Skokin's former students told me about it. Okay, I just memorized the rule before, but anytime something simple can help us remember, it's good. Okay? Notice here, the bigger degree is on the bottom in part A. Okay? If the degree is bigger on the bottom, our asymptote was y equals 0. Okay? Hunter, join us. Thanks. So, that means if it's bigger on the bottom, it's 0. Okay? Here, if it's bigger degree on the top, we have no asymptotes. Okay? So they learned Bobo Botten. Okay? Bobo Botten. Bigger on the bottom, you have 0 for your asymptote. Okay?
We did that. Go back.
How many of you remember from last year? Okay? A few of you. Good.
Ryan is afraid to raise his hand.
All right.
He said he's going to beat him up after class.
Alright, so Bobo-Botten. It's kind of ridiculous, but the more ridiculous it is, the easier it is to remember, right? So, Bobo-Botten. Bigger on bottom, you have 0. Bigger on the top, you have none. Okay? So, hopefully that'll help you remember. Well, let's look now at what happens if we do have a common factor. Okay? If we have a common factor, we have what's called a point discontinuity, or a hole. There's a hole in our graph. Now, everything else we will do the same. But what we want to notice here is if I look at this original function, and I were to factor out these two polynomials, I have x squared plus x minus 2, and that will factor into what?
X plus 2, x minus 1.
Good, x plus 2, x minus 1. And the denominator, x squared minus x minus 6, is?
X plus 3, x minus 2.
Swap the signs. X
Minus 3. Oh, minus 3.
Minus 3. Yeah, there we go. And x plus 2. Okay? X minus 3 and x plus 2 to get our minus x in the middle. Okay? So you notice, remember the rule up here for a rational function was that we cannot have any common factors. So those rules that we had learned, we can't apply yet until we deal with those common factors. Okay? So, what I could do is I could take these two common factors, and since I have multiplication now, they're factored, I could rewrite this function as what?
X minus 1 over x minus 3.
Good, x minus 1 over x minus 3. Okay? X minus 1 over x minus 3. Now, believe it or not, we're actually going to use both the non-factored part and the factored part to help determine these solutions here. Okay? Now, first of all, if we want horizontal asymptote to determine if there's a horizontal asymptote, that required us not to have any common factors, right? So I'm going to look at the x minus 1 over x minus 3. All right, so there, what do I get for a horizontal asymptote? 1. All right, they're equal, so I use the ratio of the coefficients, so it's 1x over 1x, 1 over 1 is 1. Okay, and I'm going to sketch this as we go, as we find stuff. All right, so now I know that y equals 1 is, let's do that actually, a horizontal asymptote. Okay? Mostly horizontal asymptotes. Okay? Now we need to determine the domain. We want the domain of the function, right? So we should use the original function, not a reduced form. Okay? So our domain is what? X can't be
3 or negative 2.
good. X cannot be 3 or negative 2. Now, do both of those give us asymptotes?
No. Maybe.
No. Remember our rule was that the zeros of the denominator only give us vertical asymptotes when we have no common factors. So, we need the zeros of this denominator, the x minus 3. So that gives us a vertical asymptote where?
3.
At 3. Okay? So now, let's see here. We've got 1, 2. Because we're looking at this denominator, because for it to give us a vertical asymptote, it has to come from a function, a rational function that has no common factors. All right? So now I've got my vertical asymptote here. this is where the point discontinuity, or the hole, comes into play. If you have something that was eliminated from the domain because it was part of a common factor, that doesn't give us a whole asymptote, that only gives us a hole. Alright? So the hole is going to be when x is negative 2. Okay?
Yeah, I remember that.
Now, when x is negative 2, if I plug that into my original function, I'm going to get something undefined, right? So, what am I going to have to do to find out where this hole is? Plug it into the reduced one, okay? So I plug it into the reduced one. Negative 2 minus 1 is negative 3. Negative 2 minus 3 is negative 5. So that's a positive 3/5. Okay? So the point negative 2 3/5 is a hole on my graph. So let's get that here. Negative 2 3/5 is a little over a half. And actually, wait, I need to make it a hole. So I'm not going to put a whole point there. I'm just going to put an open point there. Okay? So my graph is going to go through that location, but there's a hole there. Okay? And then also, I can tell my zeros as well. What are my zeros going to be?
1.
Just at 1, right? Because x is not allowed to equal negative 2, right? So it's my 0, there's actually only 1 in this case, is x equal to 1. Alright, so I can put that on my graph as well. Okay? Now if we keep in mind what happens with our horizontal and vertical asymptotes, we actually can sketch this whole graph. Okay? I know since I'm below the horizontal asymptote over here that I'm going to be approaching the horizontal asymptote from the bottom on this side. Okay? And also, it can't go up, so it's got to approach the vertical asymptote on the left by going down to negative infinity. What's going to happen when it gets to the other side of that? It's going to jump to positive infinity, okay, because there was no multiplicity here with our vertical asymptote. So it jumps up to positive infinity, comes down, and then it's going to approach that horizontal asymptote as it goes, as x gets bigger and bigger. Okay, so that's what that graph would look like. Yeah, Callan?
Why is it 0, 1?
The 0 is 1 because that's what would make our whole function equal to 0. You want the numerator to equal 0 to make the whole function. Whoops. So x would equal 1. Okay, so you'd have 1 over, technically you'd have 1 over negative, or you'd have 0 over negative 3, which would still be 0. Okay. Okay, any other questions? So listen, it's not too complicated, there's just a bit to remember. Okay? There's a bit to remember, and part of that is how the graph behaves around the asymptote. Okay? Now, on Monday, we're going to look, what I want you to do over the weekend is practice a little bit just with these graphs, finding your horizontal and vertical asymptotes, finding holes, and then on Monday, we're going to look at one application problem related to this. You know, how that can be used to interpret a situation. And then also, we're going to look at slant asymptotes, which, believe it or not, you already know the mechanism for finding them, you just have to know that you need to use it. Okay, we're going to actually use polynomial long division for it. So, But those only happen in one specific situation. So we'll be looking at those briefly on Monday, and then we'll do some extra practice. And then again, Tuesday we'll review at the first half of the period, and then you'll have your test second half, or second 2/3 probably. Might give you a little extra time. Okay? So, for the practice, here you have some matching, okay? As you're looking to match, pay special attention to the equations and what the asymptotes would be, okay? Look at where the asymptotes are in the graphs, and look at what the asymptotes would be from the function. And then, you've got a few here. Identify horizontal and vertical asymptotes, identify the holes in the graph, okay? And then, you actually could just, rather than using a table even, you could use your graphing calculator to verify, okay? Alright, so, that's it for today.